Hey, what's up? I'm Dave Boyer, aka Mr. Boyer, aka the Swamp Man. I'm here in my Boyers Park studio at my house, home from the school shut down due to COVID-19 coronavirus. So we're making do with things here. And I'm trying to keep teaching lessons. So this is the second of the earthquake lessons. The first earthquake lesson, what we were trying to get at was the movement of the plates and how each different plate boundary, whether that's convergent, divergent, or transform boundaries, all can cause earthquakes. So we have different types of faults, different types of stresses from each of those. That was that first video that you should have completed already. So in this second video, we're kind of going to analyze what an earthquake really is. Earthquakes are waves. Earthquakes are wave energy that move through the earth and on the surface obviously can cause things on the surface to move, buildings to fall down. Hopefully no loss of life, but it does happen. So I'm going to start off by kind of changing one of the words that I've been using, and that's the word earthquake waves. Instead, we're going to be calling those seismic waves. So again, if you see the word seismic, you need to be thinking earthquake. Seismic waves. So seismic waves are propagated. That's a weird word that they like to use in earthquake and science terms. Propagated just means that they are created there and they spread out from there. So seismic waves are propagated at the focus. One of the first parts of this earthquake assignment was you're supposed to kind of learn some differences between two words. So we have the word focus and epicenter that are key words in terms of an earthquake. The focus is the actual spot inside of the earth where the shifting of the rock or the earthquake happened. The epicenter is the spot on the surface directly above the focus, the closest place on the surface in relation to the focus. So if we're talking about where an earthquake happens, that's the focus. And if we're talking about how it might impact us on the surface, we should probably be using the word epicenter. So this is one of my new ways of trying to teach this, and tried to kind of introduce this phrase that seismic waves come in the 2 by 2 by 2s. So 2 by 2 by 2s have to do with these three different levels of waves that we're going to look at, or three different kind of categories, and they're each broken into two categories within them also. Hopefully that'll make more sense as you start to see these and I get through all this video. So here's our first two. There are two types of seismic waves. And I think this is actually really easy to understand. We have body waves and surface waves. Body waves are inside the earth, and surface waves are on the surface. Hopefully that's pretty easy to understand. Body wave inside the body of the earth. Surface waves are happening up on the surface. So now we can start to break those down into the next twos. So within body waves, we have two types of body waves. There's a lot on this paper. I'm planning on posting these notes on the Power School page, so you shouldn't need to copy them down, but if you can read it, you could pause it and write it down from there. But there are two types of body waves. As we go through some of the key characteristics of these two types of body waves, we're first going to name them and then talk about their speed, also the movement that they are causing the rocks to do as they travel through them, and then comparing them to some things that we studied way back in first quarter with other types of waves like sound and light, or longitudinal and transverse waves. So the first type of a body wave is called a primary wave. Primary wave, not that primary is a big word, but in geology, they've liked to shorten that to just call them P waves. The P stands for primary. The reason that they're called the primary waves, if I think of primary, like primary school is like kindergarten through sixth grade. Usually we don't really use those terms in North Carolina, but primary is the first school you go to. And then you have secondary school, which is mostly the high school, but some of them include 7th through 12th grade. So we'll talk about secondary waves in just a minute. But for primary waves, our key term there, primary, means that they are going to be the first wave. So it's not that they are the first wave that's made in the earthquake. It's that they are the first wave that's going to get to the surface. So if these two types of body waves both happen at the same time, at the instant that the earthquake happens, these two types of body waves are shot through the ground of the earth, through the insides of the earth. Why would a P wave get to the surface before the other type of a body wave? Well, the answer's got to be that it's going faster. So P waves are the fastest of the two types of body waves, and that makes them the first to reach the surface. Our second type of wave is called secondary waves. And secondary waves are called secondary because they come second. They arrive at the surface second because they're moving slower than the P waves are. So we look down here, we got our secondary waves, aka S waves. And they are slower and they arrive after the P waves. So before we talk about the other parts of the notes that I have there, we're going to kind of address these two different speeds of these two types of waves. I'm going to try to move over here to a really ugly drawn map of the United States. It's not that bad, but I've definitely done better. So one impact of P waves and S waves traveling at different speeds, when the P waves arrive at the surface first and the S waves arrive second, is that stations that are set up to monitor earthquakes, and we have thousands of these stations spread out around the world, they're going to receive information on a tool called a seismograph. So a seismograph is going to measure the shaking of the ground. So before the earthquake, the seismograph's not really going to be reading much shaking of the ground. But the first wave that arrives is going to be the P waves. And those P waves are going to move the ground. They're going to be recorded on the seismograph. And then there'll be a delay, a period of time in between the P waves and the arrival of the S waves. And then those S waves can fade after the earthquake's done. So we have P waves and S waves that arrive at different times. Well, mathematicians can take those times, the difference in the times between the arrival of the P wave and the S wave, and figure out how far away from that station that earthquake's epicenter was. So let's say we have a station measuring here in Kernersville, North Carolina. And they get their readings of P waves and S waves. They put them into the mathematic formula, and the formula says this earthquake happened, let's say, 500 miles away from Kernersville. Well, we don't know if that earthquake was 500 miles off to the Atlantic Ocean, 500 miles north, 500 miles west. Like, we don't know which direction it comes from just by doing the math of the difference in time. But what we can do from that is set up a ring that represents all of the possible locations of that epicenter. It had to have happened somewhere on this circle, which every spot on that circle is 500 miles away from the measuring center in Kernersville, North Carolina. Once we have one city, that's not going to give us enough information, obviously. As you can tell, it gives us basically an unlimited number of options of where that epicenter could be. So we might coordinate with another city and their seismograph. So let's say a city in Dallas, Texas, somewhere around there, I guess, records their information. They receive the P waves. They have a period of time between the P waves and the arrival of the S waves because the P waves are faster moving than the S waves. And they do the math and find that the earthquake happened, I'm just making up numbers here, but let's say the earthquake happened 300 miles away from Dallas, Texas. Well, again, we don't really know where that epicenter is. All we know is that it's somewhere in a radius of 300 miles away from the seismograph station. So if you can see our circles here, if we have two circles, two different measuring places, then we're looking for anywhere where they intersect together. And you can see it could be here off in the Gulf of Mexico, or it could be up here in the Midwest. So we don't really know which of those two places it's at until we use a third station. So this method is called triangulation. If you think of triangle, you should think of three sides, right? So triangulation is going to be using three locations to find the exact epicenter of the earthquake. So we're going to consult with another city. And let's say we're going to consult up here with Chicago, Illinois. And Chicago, they've received their data. Their seismograph has graphed out this earthquake wave as it's come towards their recording station. And then they do the math and find out that the earthquake happened 50 miles away from Chicago. And then we start to plot out Chicago's radius of 50 miles. And it has to have happened somewhere on that red circle, but also somewhere on the blue circle, and also somewhere on the black circle. And there's only one place where these three circles intersect together, and that is right here. So that's the method of triangulation, and that tells us that the epicenter of the earthquake is located at that spot, at the intersection of the three possible rings that earthquake could occur in. So that's one way that we use these two types of body waves, P waves and S waves, to learn more about an earthquake. Once we identify the epicenter of the earthquake, we can then hopefully send rescue in. They're going to realize that the most damage is going to be at the epicenter. So it can be used to hopefully save lives, but also just to understand more about what's happening beneath the earth where we can't see. So speaking of what's happening beneath the earth where we can't see, the next piece of information we're going to talk about with body waves is the types of rock or the types of medium matter that a wave travels through, the types of medium that each of these types of waves can move through. So going back to looking at P waves, primary waves, what I put on here is that when they are moving, they're going to push and pull the rock as it moves through, just like a sound wave does, which means that P waves and sound waves are both longitudinal or compressional waves. When we studied sound in first quarter, one thing that we tried to make a big point of was that sound must have a medium to travel in. Otherwise, it can't push and pull the molecules back and forth, crashing molecules into each other and passing that sound energy on from one molecule to another. Well, P waves are pretty similar with that. They can only move through solid rock and liquids. Once a P wave were to, say, go past the surface and reach the atmosphere, it's not going to be able to move through air. So planes flying over an earthquake aren't going to get shaken up by the earthquake because the atmosphere is not affected by that. But the P waves can move through solid rock and they can move through liquids. And we'll see why that's important in just a minute. Back to our S waves. S waves only move through solid rock. S waves cannot travel through liquids. So that brings us to another idea of how this can help us understand more about the earth below our feet. So I've tried to draw down here a quick representation of the layers of the earth. So we have the inner core, outer core, mantle, and crust. And understand this, we definitely need to know what those different layers are made of. The crust is made of solid rock. The mantle is made of kind of a weird state of matter. It's sometimes described as plastic-like or near solid or near liquid. It is able to move. It's pretty free-flowing, as we've talked about with convection currents, but the molecules are pretty close together. And then we have our two cores. The outer core is liquid metal, and the inner core is solid metal. So the way that we've learned this is actually by studying the movement of P waves and S waves through the earth. So I'm going to try to draw something that would happen during an earthquake. So we're going to pick a spot somewhere in the crust. All earthquakes happen in the crust, and then those sends wave energy, P waves and S waves, or body waves, through the earth and up to the surface. When body waves reach the surface, they turn into surface waves. We're going to look at those next. But as they travel through the earth, they're going to push and pull the rock. The P waves are going to push and pull the rock back and forth as the wave energy moves through them. So P waves are going to move in all directions through the earth. If we were to track the movement of a P wave, it might flow this way. It might flow this way. It's going in all directions. So if we were just to look at the crust and mantle, the crust and mantle are both behaving as solids. The crust is solid and the mantle is going to behave as a near solid rock. But these P waves that enter the outer core, can they go through the outer core? Well, what we've said so far about P waves is that they can travel in both solids and liquids. So as it enters this outer core, it's able to keep moving through it. Now, often as these P waves are coming through different mediums, they're going to change speeds or change directions. So they do bend a little bit differently through these different layers. But in general, we have P waves able to pass through all the layers of the earth. So if we have a recording station reading earthquakes up here and recording stations down here, they're going to be able to record P waves. There's only a few places where, based on the refraction is the bending of a wave, like the bending of light, or in this case, the bending of a P wave. So refraction can create shadow zones, typically one on each side opposite from that earthquake. A shadow zone is a place where none of the waves reach the surface. They've been bent away from there, so they're not able to travel all the way through the earth and reach the surface, even though P waves can travel through each layer of the earth based on their states of matter. Now, where that changes is when we look at S waves. Quick review: S waves are going to be where they can only move through solid layers. They cannot move through liquids. So they're going to start in the same spot wherever that earthquake happened, and those S waves are able to travel through the mantle without any problems. Able to travel through the crust, again, because the crust is solid and the mantle is acting as a near solid rock. But the problem with shadow waves, or the thing that arises, is as those S waves enter or head towards the outer core, that outer core is liquid metal, and the S waves cannot travel through there. So S waves, we get this huge area on the other side of the planet, this whole shaded in area over here. No S waves can reach that side of the planet, because to get there, they would have to go through the outer core. And S waves cannot travel through liquid layers. So it can't travel through the outer core. So the S wave shadow zone is huge. It's the whole entire other side of the planet, basically. whereas P waves can travel through the outer core, travel through the inner core, and the only reason they have shadow zones at all where there's no wave energy that can be recorded is because of the refraction going through different mediums. So those are our main ideas with the body waves. Kind of quickly looking back through here, P waves are the fastest. They're the first to reach the surface. S waves are slower. They arrive after the P waves. And then as they reach the surface, body waves turn into surface waves. And that brings me to my last of the 2 by 2 by 2, and that is surface waves. So far we've had 2 types of seismic waves, body waves and surface waves. We've had 2 types of body waves, P waves and S waves. And now we're going to look at 2 types of surface waves. And these surface waves are named after scientists that studied them. The first one's kind of strange because most people don't think of love as a name of a person or a last name of a person. There's obviously different emotions that go with that, but the first type is called love waves and named after a scientist with the last name of Love, and the other are called Rayleigh waves. So as these body waves reach the surface and can start to cause parts of the surface to move, they're going to move based on the types of surface waves. So love waves. Love waves are the first waves to arrive on the surface. So what type of body wave do you think would turn into a love wave? The P waves were the first to arrive at the surface, so they turn into surface waves and become love waves. And love waves, because they are coming from P waves, and P waves are longitudinal, P waves are just going to get the matter to begin moving side to side. Love waves, when they're on the surface, love waves are going to cause buildings, bridges, trees, rocks, everything to move side to side. When we've engineered things, engineering stuff for side-to-side movement is actually a little bit easier than some of the other types of movements that, say, a tall skyscraper would have to undergo. So love waves are not the most damaging of the 2 types of surface waves. The other type of surface waves, the Rayleigh waves, Rayleigh waves are going to roll along the ground like ocean waves. They're going to do a combination of up, down, and side to side. And because of those combination of movements, they are much more violent types of waves. So if you imagine a building sitting here, I didn't bring a building up here and I've already started my video, so I'm just going to keep going. Let's say this is a tall skyscraper. When the love waves come, that skyscraper is going to start to move side to side like this. And for the building, it's not going to move unless it's been engineered really well to do this. It's not going to move just perfectly side to side. When the bottom of it starts to move to the side, the top of it stays in that same spot. It resists the change in movement. It's got inertia. But then as it moves back towards the other side, it kind of catches up to the top, swings back. So our building is going to kind of do this kind of motion with a love wave. And again, a lot of buildings, especially really well-designed buildings, can withstand those kinds of movements pretty well. But when those S waves reach the surface and turn into Rayleigh waves, the buildings, because they're attached to the ground, are going to start to do this sort of rolling motion. They're going to be moving up and down, but also left to right at the same time. So they are kind of rolling around, and that's a whole lot of different directions of forces that are acting on the objects. And because of that, especially a really tall building, if it was poorly designed for this and has no way of kind of counteracting the forces here, it's not going to be able to withstand this kind of multi-direction forces. And because of that, most buildings that collapse during earthquakes collapse because of the Rayleigh waves. So there's a whole lot of information there. It's a long video. I'm sorry about that, but just wanted to kind of get through a lot of that. and look at this new way of teaching it, for me at least, that seismic waves come in the 2x2x2s. We have two types of seismic waves, body waves and surface waves. We have two types of body waves, P waves and S waves. And we have two types of surface waves, love waves and Rayleigh waves. It's really cool stuff. The more you learn about earthquakes, I think the more we understand what's going on beneath our feet, and the more that we can start to prepare and change kind of how we design buildings and how we live our daily lives to survive in areas where earthquakes are really prevalent. We're really fortunate in Kernersville to not be on a fault zone, not to be on a plate boundary. We don't experience big earthquakes like this. But other cities, I keep my family, close to heart always. And my brother and his family lives in San Francisco. They've been through lots of earthquakes there, and luckily not a really, really, really big one yet. But I can only hope that their house has been designed well and that they are in a safe place for when that big one comes. So just want to stop and share a little bit with you and tell you that science rocks. Peace.